Okay, good afternoon. Today's space engineering lecture pertains to NASA systems engineering project formulation. So I'm going to cover two aspects of this. One is the initial aspects of space systems engineering, kind of a continuing the overview from last week. And then I really want to get into the vision, mission, goals, and objectives as part of project formulation, but also in general how it's used and how you might use it in your development of research or projects or whatever the case may be. So last week we talked a bit about the design phases: pre-phase A, phase B, phase C, phase D, phase E, and phase F. I'm not going to go into detail over them again. This is a recap from last week. It talks about pre-formulation, and that's really where we're going to focus on. And the next few lectures will also be focusing on this as well, as we really try to focus in on conceptual studies and then conceptual designs and technology development. So for systems engineering, the part about system design and definition is really first understanding the stakeholders' expectations, definition, and the management portion of it. Then you get into defining and understanding the technical requirements definition, which is really about transforming those stakeholders' expectations into unique, quantitative, and measurable technical requirements. And those are really expressed in shall statements. We'll go into more detail later on that. The next step is really about logical decomposition, really transforming the technical requirements and the user and stakeholder expectations into kind of a functional logical decomposition, really looking at the lower levels of detail and how those are broken out by analyzing the function, time, behavior, data flow, the objects, and other models. And then you get into your design solution definition, where you get into your trade studies, your analysis, and really the full technical data package describing your selected solution. And that really, then you get into understanding and description of those solutions, whether you're going to make it, buy it, reuse it, those specifications and how those impact your decision making. So you can see there's kind of a flow here, and I'll show you some graphics to further define that. But there's a flow of stakeholders' expectations, understanding what you're designing, why you're designing it, transforming that into requirements, logical decomposition into functions, and then getting into design solutions. Then you move into product realization, and it's really that is where you start to really focus in on the product implementation, the integration of the product, understanding the verification and validation, and then transition of that product into use. So here you're really focusing on that product implementation from the standpoint of that specific product through buying, making, or reusing to satisfy the design requirements. And thus, you haven't, in the first step that we talked about just a minute ago, you really hadn't really designed anything yet. You begin to conceptualize maybe a little bit, but you really need to understand requirements and functions and interfaces and so on before you can jump into designing something. A lot of times we tend to want to jump right into the fun stuff, which is designing, before we really understand what we're designing. A big part of this is the integration function, which, systems engineering and integration, that's the key aspect of really forcing the integration of the higher level into the lower level products and the lower level systems, subsystems, and components of the subsystems, so you understand the interdependencies and dependencies between all the different moving parts, so to speak. That really is not just on the product, but also the strategy, detailed planning, integrating across the products, integrating across elements and systems, and confirming that these products are ready for integration, and understanding, the operations of the system in that environment. Verification really is about proving the end product conforms to those requirements. So usually when we write requirements, we also write our verification statement, and requirements should be quantifiable, not vague. And sometimes we tend to also write two requirements in one, as opposed to keeping them simple and focus on a specific task of that product, what it's to do. And so verification is usually written when you write the requirements, and is an important part of that process of proving that the end product conforms to the requirements. And that proving part is important when it comes to your certification products and your data for certification. Validating that product is really conforming that a verified end product satisfies the stakeholders' expectations for the intended use. In other words, you validate that the concept will operate as expected in that environment. So you tend to validate concepts of operations. You validate the product meets stakeholders' expectations, or the end user expectations, and ensuring that any anomalies discovered through this validation process are resolved. And then product transition really is transitioning the verified and validated products to the customer for the next level of system structure, which usually is use, whether it's use in space or use on the ground or use in training, whatever the case may be. But you want to transition that. And so really that includes understanding handling, storing, shipping preparations, how it fits into the various shipping products, how it's handled, and the documentation to accompany it. Then you get another part of this is that technical management. So we were just talking really mostly about the design, development, integration, testing, and use of a product. But in parallel with all that, you have the technical management that parallels those activities, from the technical planning, requirements management, interface management, and technical risk management. And this is a bit more detailed and complex, and really I recommend you take training courses or do more research on project management. But this gives you an overview that the technical planning really is focused on the systems engineering management plan and other technical plans, your aspects related to the application management of the whole process, as well as identifying, defining, and planning the technical effort necessary to meet all those project objectives. So it's a bit more than the actual technical work, more than just the CAD work or the analysis. It's really getting into that cross-cutting effort of planning and implementation of that plan. So it would, part of it requires determining, the deliverable work products from a technical effort, identifying technical reporting requirements, identifying entry and success criteria, evaluation criteria, the product and process measurements that you would use, and so on. So it's a cross-domain interoperability effort. And also there's the aspect of data management, versioning and control of the data, and making sure that everyone is using the right and up-to-date data set, requirements, CAD models, etc. Requirements management is just that. You're managing the requirements, so you want to really manage that product requirements, including bi-directional traceability. And that's the key word, traceability. You want requirements to have traceability up and down the chain. So requirements flow down, you verify up. So in a V shape, and I'll show you that later on. But there are a variety of management tools or requirements tools that can be used for this process, and you have those. You make sure that each requirement has a parent requirement and if it doesn't, then it's an orphan. Some requirements are allocated or directed to the project, and some are derived from analysis. And we could talk later on that as well. But really, that requirement traceability is important, that every requirement has a parent requirement, and then if there are children requirements, you have traceability downward as well between all these requirements. As equally important in all this is interface management. The identification of interfaces, and it can be in many forms, not just the technical interfaces, but also understanding the interdependencies of those interfaces and then managing that and controlling that. And that's where you get into documents like interface control documents and so on, which basically baseline and lock down, this is what we know to be the interfaces. Here are the inputs and outputs between these interfaces and the expectations between the various products that are interfacing, whether they're at the element level, system level, subsystem level, even down to the component level. And then you have technical risk. And technical risk is that aspect of understanding all the technical deviations from the plans, identifying technical problems before they occur, which is usually done with a preliminary hazard analysis, planning, invoking, and performing these risk handling activities, and then managing it, documenting it, baselining it, managing it, understanding your mitigation plans, and then also putting in controls. And you can read the rest on that and what those triggers are that would implement either a contingency plan or a control to mitigate that risk. And a lot of this can be found, as you can see over here on the right, the NASA Systems Engineering Handbook. There is still continuing, there's still more technical management aspects of configuration management, the technical data management, technical assessments, and technical decision analysis and decision making. I'm going to focus on the technical assessment and decision analysis right now. Really, the technical assessment really is that aspect of the analysis in support of the system design, product realization, and the technical management efforts. And really, it takes into assessment of strategies and policies, as well as the technical work product and productivity, and the product quality tracking, and technical metrics and reviews as well. And the reviews can be in peer review, technical reviews, and life cycle reviews. And as part of that is understanding your success criteria, the evaluation criteria as well, in assessment of these the technical work that you do. As part of that is really the decision analysis and decision making. And that is aspects related to technical decision issues, identifying decision criteria, identifying alternatives, analyzing those alternatives, and then selecting those alternatives. As we mentioned, or I mentioned last week, it's really important to knowledge capture your decision making, not just the decision making, but the process by which you do it and your evaluation criteria. And that's so important because it helps you to defend the decisions you made. Now, not everyone will necessarily agree with your decisions you made, but when you do make these decisions and you have this to back it up, then you can say, okay, this is what I did and this is why I'm sticking to this. Folks can disagree with that, and you can have a intellectual, meaningful conversation related to why they disagree or whatever the case may be. And maybe they have a different viewpoint, or maybe they have a different evaluation criteria that you should consider. So this is that design process, kind of what we just went through talking about. You have your mission authority or your start. You have an understanding of stakeholders' expectations, mission objectives, the constraints, test objectives, operational objectives, and your success criteria. That's your high-level project formulation. Part of this will also be the vision, mission, goals, and objectives that get developed or defined in this process. You will then, from that, develop high-level requirements and then continue to develop requirements level 1, level 2, level 3, and so on. From that, you'll begin as part of the process. Some of this is in parallel or sequential, that you do your function and logic decomposition. What are the functions? What is this widget or this component or system supposed to do? Understanding also users. How are the users supposed to use it? Doing that human system integration or human-centered design. And you got to think about all the aspects of the interactions, not just the end user, the astronaut, or whatever, who the end user might be, but also the people in manufacturing, in testing and integration and assembly, in shipping, in launch, etc. Once you have at least an understanding functionally, then you can really begin to understand and set up your trade studies. And this is an inner design loop. You do your design and product breakdown structure. You derived and allocated requirements, as I mentioned before, which are requirements in the sense of functional requirements, performance requirements, interface requirements, operational requirements, and the ilities like reliability, serviceability, etc. And from that, you derived a concept of operations, a ConOps. And that's really kind of a written description of how you intend to use this product, how it's intended to go through its life cycle. And you may not even have any design yet, but you have an idea of its function, you have an idea of how it's going to be used, and in a time sequential step through of a kind of a storyline, if you will. From that, you will get into functional performance analysis, assessments, and analysis of the system design with different options, different subsystems. You will have to assess, is that sufficient in depth? Are we done, or do we need to go the next level, or is there something missing? Did something not work out? Do we need to change out a subsystem or something else? And then you would iterate. Or you will go on to the next level and say, well, is there more work to be done? Is this safe? Is it reliable? Is it affordable? All part of the analysis, in which you can then say, well, we need to reassess our requirements and rebaseline them and start over and challenge some of the previous assumptions and requirements, or you're done to this point and you go ahead and baseline it. And you can see here's the different color coding that relates to this. This chart will get used, I'll show this over and over, but it gives you just a high level kind of conceptual design process, system design process. So this is really focused on the mission and system definition flow. Similar to what we just talked about, the mission authority, mission objectives, mission requirements, and then that's more from the customer level. They give you programmatics, cost, schedule, constraints, mission classifications and objectives. Then you get into your implementation from the organizations, your system level functional and requirements development definition, looking at the environmental and other constraints and requirements that are inputs, institutional constraints, your assumptions that go into it, and then you get into your system level requirements definition, and then further break them down into subsystem levels, and further break them down into allocated and derived requirements. So through your system analysis, you may come up with derived requirements. When we were doing the habitat demonstration unit, we were testing various concepts of operations, and we let requirements float so that we could further understand them before we nailed them down. And partly why you do testing and design and test and so on is to further understand, do I have good requirements, or did I derive some new requirements that go beyond what you had before? You still have to have that traceability up and down the chain as far as requirements. This is a similar look to the previous one, just a different way that they looked at it. I'm not going to go into it again. It says the same thing as the previous prior slide. So system design keys. You want to have a successful understanding and defining the mission objectives. And that's why I mentioned mission objectives early on. And really, you want to understand also the test objectives. How do you know when you've met your mission objectives or your test objectives? And also the concept of operations in capturing the stakeholders' expectations, which will translate into the quality requirements and operational efficiencies of the life cycle of the project. You want to have complete and thorough requirements traceability. That's a critical factor in validation of the requirements. You want to have clear and unambiguous requirements to help avoid misunderstandings. In the commercial crew program, we purposely went with a little bit more vague requirements to allow the contractors or vendors to have more flexibility. Would everyone please mute? To allow everyone to have flexibility into their design process, but they interpreted some of the vague requirements in a way that was going to be unhealthy to fly astronauts. So we had to be more specific. We had to come back in, which caused, as you remember from last week, caused slippage and also cost overrun because of change in requirements. Anytime you change a requirement, the contractors will come back and say, but you changed your requirement, we need more money. So, also you want to document all your decisions made during the process, and the validation of the design solution is a continuing, recursive, and iterative process. So this is the system design process from a stakeholder expectations definition. So from the project, you're going to get customer expectations, other stakeholders, and then customer flow down requirements. And as part of this, you should also be pinging the users or astronauts. And so from this process, you will go through a series of steps of establishing a list of stakeholders, who they are, make sure you cover and stakeholders can also be manufacturing, can also be the launch folks, it can be the launch integration folks, it can be the training folks, it can be the end users or astronauts. So it's not just the astronauts. You establish the operations concept and the various strategies. You define the expectations and acceptable statements. You analyze those statements for measures of effectiveness, which will then turn into your evaluation criteria or your criteria. You validate that your defined expectations reflect bi-directional traceability. Then you obtain stakeholder commitments that they buy in. Basically, you reiterate what you think you heard from them, and they say yes or no I really meant this. And then you baseline those stakeholders' expectations, and you capture those work products. What comes out of that? Validated stakeholders' expectations, a concept of operations, enabling product support strategies, and measures of effectiveness. This is kind of examples of stakeholders throughout the life cycle. I'm not going to go into detail on this. I think pre-phase A and phase A is kind of really where you want to look at that and look at all the different types of stakeholders that you might need to be having conversations with. Obviously, this is NASA centric, heavily NASA focused, as opposed to like a SpaceX or Blue Origin. But even them, they have NASA involved if NASA is a customer. If NASA is not a customer, then they have NASA from a different perspective as stakeholder in the sense of NASA oversight from astronaut or health and performance of humans. And who's responsible for that, right? For space. Here on Earth, it's a combination of oversight regulatory commissions that are involved from the U.S. perspective that have responsibility for health and oversight of humans, whether it's medicines or buildings. Buildings have codes for a reason. Anyways, so look at this when you get the time and look and think about how those stakeholders change through the life cycle, but also they're consistent through the life cycle, but their relationship changes. And so when you do this, think about it from the standpoint of each phase or life cycle. all the way through disposal. So stakeholders have informational flow, and you have it from the standpoint of left to right and right to left. And so from a mission goals perspective, you have agency strategic plans, announcements of opportunities, technology roadmaps, and directed missions. Then from your mission objectives, you have all of these types of objectives that can be influenced or part of the stakeholders' information. Then you have operational objectives and success criteria, and then design drivers. And you'll understand, and as you move forward, and especially with Olga's class, you'll get to better understand what's driving, what are the mission drivers, what are the success criteria. And that's really what I want you to take away from this, is understanding that there are various design drivers from, and another one that should be here is the environment. The space environment is always another design driver. This is a kind of a process overview of the requirements flow down and product realization. So requirements flow down to technical solutions, to the lower level of the design process. You have the technical management process, which covers all aspects of the planning, the management of all the different data, risks, requirements, and configurations, the assessment process and decision making, and then product realization, verifying and validating the requirements meet, or the product meets the requirements. So that flows back up to the realized product and certification of that product. So this is that systems engineering engine. Requirements flow down. So you start high level requirements and keep decomposing and allocating requirements downward, parent to child, and those child requirements become the subsystem and components. And then when you manufacture and build those and integrate them, you're verifying back up. You're starting at the component level, component to component, component to subsystem, subsystem to subsystem, system to system, element to element, and so on, all the way back up to product realization. So requirements within this thing, and here's an example of their level 1 requirements, which was the exploration requirements document, and that transformed into the constellation architecture requirements document, and then down to the system requirements and the prime item specs, the preliminary design, and the end item specs, and then your verification back up through. So requirements and design. Really, requirements are what do I want and how can I do it? And then you get into integration and verification. Let's put it together. Does it all do what I wanted it to do? And these are all the steps. And then here's your different reviews across the bottom. It also is described as an engineering constant design and iteration cycle of identifying your goals, developing, creating concepts, doing trade studies, selecting the design, increase the resolution, and you keep going and going and going until you've satisfied where you think you are to the end point of you've satisfied all the requirements, you have all the functions defined, you have a concept that satisfies it, you understand it, it relates to the concept of operations, you've validated that it's expected to work the way that the stakeholders and end users think it will, and you have a verification process identified that will take the product and verify it through the various either testing or analysis and so on. So the design and definition process sort of looks like this. We talked about the inputs, all the customer, technology, looking at requirements, decision making, and so on. You get into that requirements analysis activity, which is aspects of analyzing the mission, the environments, the functions, the performance requirements, and design constraints. And then you get into the functional analysis and allocation, the requirements loop, and then you get into synthesizing. That's your design loop, which gets into verification as well. So this is your overall system analysis control of this overall activity in design definition and analysis. The output is your documented level dependent, your decision database, the system configuration, item architecture, specifications, and baselines. So this is how the DoD looks at it. It's very, very similar to how NASA does it as well. Trade studies is an important part of that analysis and understanding requirements and performance and function requirements. And so this is really similar in that you define your goals and objectives, you have your functional analysis, you define your plausible alternatives, you define your system effectiveness or your evaluation criteria, you collect the data, you establish your performances, you do the analysis, and you do the trade studies between the different alternatives. That is basically the trade study in a nutshell. Again, you want to have a method, process by which you do it consistently, and you also have your evaluation criteria by which you then evaluate your alternatives, and now you have your decision-making products that you can defend. Trade studies can be very large and timely and consume a lot of human power, but also they can be very small and short. So very early on it could be very simple, but you do want to give it thought, and when you're doing trade studies, because it's an important part of your process and decision making. So that this trade studies really is that purpose is to assist the decision making in selecting the most suitable option. And so when you have project managers and program managers and so on, they're going to want to see some of the trade studies and want to see the analysis or the evaluation criteria. They want to have an understanding that the process you followed is a good process and that the decisions you made were good ones. And so a lot of times in your design reviews, you'll have to present some of your trade studies. You may not present them all, but you may present some of them. And it's important to be able to communicate the process and your decision making. So in performing trade studies and functional allocation is particularly important to ensure that the functions of all the human roles and responsibilities system and its behavior and success are included and allocated. And so it's really that's an important part of this, and trade studies are essential in achieving product realization. They also define the emerging system at each level of the design resolution. So you may have very high level trade studies, and then as you get down to components and selecting of specific components of a subsystem, you may have additional trade studies. Here shows a trade study process at a high level. I'm not going to go into detail of this, but you can see that you start obviously at very high level, goals and objectives, constraints, and so on. Working your way down through the system, defining the assessment measures or the evaluation criteria, collecting the data on all the different alternatives, and there's a lot of different data depending on your trade study. You may even set up models and do analysis and run models, assessments on that particular trade study, looking at performance and how that performance affects across the entire system or element. And you continue that process. Mission success criteria is important because it helps to define what the mission needs to accomplish to be successful. And this could be in the form of science missions, exploration concepts for human exploration, or even technological goals for technology demonstrations. Measures of effectiveness is the measures of success that are defined to correspond to accomplishment of the system objectives as defined by the stakeholders' expectations. So you can see how there's interdependencies in the whole process, how important understanding vision, mission, goals, and objectives and stakeholders' expectations are. Verification and validation are different. Verification is really that aspect of verification testing linked to approved requirements. such as your system requirements document, and it can be formed at different stages of the life cycle. Verification tests are the official for the record, as I mentioned earlier, as part of your certification of the system. And verification tests use instruments and measurements and are generally accomplished by engineers, technicians, operators, maintainers, test personnel. Validation really relates back to the concept of operations document. Your validating testing is conducted under realistic conditions or simulated on the end item product to determine the effectiveness and suitability of the product for use in emission operations by typical users, and to evaluate the results. So you're validating the concept of operation for the use of that product in that environment. You're verifying that you've met the requirements for the system. Here it goes into different aspects of verification, qualification, acceptance, and certification. I'm not going to read through all that. I'll let you come back to that at another time. Just knowing that, verification is part of the process. Qualification is ensuring the flight unit design will meet functional performance requirements. Acceptance is a smaller subset, usually selected as criteria for acceptance in the program, and is performed on each of the flight units as they're manufactured and ready for flight operations. And then certification is that audit process by body of evidence that you verify all the requirements have been met. There are different types of hardware. There's breadboard, brass board, engineering units, prototype units, qualification units, and proto-flight units. Now I'll let you read those over at your leisure, but just know that qual units are the units that are flight units and are the same as flight units, that they will be exposed to extreme environments. So you don't necessarily fly. You don't want to fly a qual unit because you're going to take it to extreme environmental testing. And they typically are not flown due to the off-nominal stresses you put on it. A proto-flight unit is basically a unit that or a project that has decided not to develop qual units. They're going to take the qual, or basically the proto-flight unit, and use it they'll do limited qualification testing, but they're not going to test it to the extreme as the qual unit would be, and then the unit is flown. So there's a little bit higher risk involved with proto-flight units. It's a little bit cheaper process, but in the long run, from my experience and from NASA, there can be challenges in that systems will fail, or you didn't necessarily ring it out like you did the qual unit, and thus later on you end up having to replace it or redesign it. There's 4 different methods of verification: analysis, demonstration, inspection, and test. And they are just as they sound. So I'll let you read those at your time and at your leisure, as I need to really move forward here. And then there's system engineering analysis types. You got failure modes and effects analysis, preliminary hazard analysis, event sequence diagrams, human reliability analysis, and sparing and logistics analysis. And this really helps you to assess all the different aspects and analysis of the system as a whole, but individually as well. And the human system function allocation is important, making sure that all the different aspects of the human as a system are allocated through the life cycle of the system or product that you're trying to realize. And there's also usability evaluations and designs, and that's part of the human system integration function. And functions are allocated to combinations of the hardware, software, and the humans, and then assumptions are assumed about the specific roles and duties of the human in the system through the whole life cycle, not just the end state or the end use. User analysis: see the spaceflight operations tasks throughout the life cycle through the astronaut's eyes. So you want to view it as through the user or the astronaut. What tasks are performed, what tasks need to be done, what tools are needed, will it take more than one crew member to do it, Is there going to be a robotic assistant involved? Is there sufficient workspace? Is there sufficient human access to the task area? Is there sufficient time allocated? Human-centered design is an important part of that as well. Identifying all the analysis is similar to the system work that you've done or would do. And then identification of all those human capabilities and their limitations in the mission context. I'm going to skip the task analysis. This is getting into more details about specific tasks. Here's a reference on life support analysis, giving you some of the baselines and assumptions that provides for analysts, modelers, and others related to life support. In other words, how much consumables humans need, how much CO2 is given off, how much oxygen you need, food, water, etc., how much feces or urine you would be giving off, and other assumptions and baseline values. So now I want to get into defining the vision, mission, goals, and objectives. This is really important. I think part of understanding conceptual design and early definition project formulation. It relates to your design reference missions, it relates to your concept of operations, it provides that top level design concept. DRMs, your design reference missions, are those high level understanding of your mission flow. It helps to identify the major functions, determines many of the constraints, and the concept of operations then define the specifics. And then you have your requirements flow down. So the vision, mission, goal, needs, goals, and objectives come from the high level, or you develop them. From that, you derive your exploration architecture requirements, your concept of operations, develop your design reference missions, and then from there you derive and allocate your program and element requirements. So it's really in this area that we're talking about as part of that process. I'm going to skip this and this, as we've already talked about it. So the initial steps of defining a project is establishing a vision statement, from that defining a mission statement, and then defining your needs, goals, and objectives. And objectives relate to your goals. So you perform a stakeholders analysis, understand those stakeholders, develop concept of operations, develop your alternative architectures and scenarios. And a lot of this is driven by an understanding your vision, mission, goals, and objectives. And you'll have science objectives, and what those design drivers include, you can see here, there's a lot of them. And then you'll have exploration objectives, or mission objectives. And there's a number of design drivers that influence your exploration mission as well. So the vision is a big picture of what you want to achieve. It should be inspirational, a vision of the future. A mission or mission statement is a general statement how you will achieve the mission. So maybe the vision is enabling humanity to become a multi-planet species. That's one that I've used before, or I do have on my website. So my mission is to design exploration habitation capabilities that support humans living on the moon, Mars, and deep space. Strategies are one or more ways to use the mission statement in order to achieve the vision statement. Goals are the approaches for accomplishing the mission. These are general statements of what needs to accomplish. So a goal for the mission of designing habitation for deep space, a goal would be one goal might be to develop in situ manufacturing capabilities, or to develop pharmaceuticals for humans to be productive in space for long duration. To develop, a goal might be to develop radiation protection aspects, or so on. I think you get the idea. Objectives are the tactics for accomplishing that goal. They're specific to that goal, and objectives provide specific milestones with specific timeline for achieving a goal. So if one of the goals was development of radiation protection capabilities, then an objective would be to define radiation limits for crew members for long duration by, in the time frame of 2030, to to develop radiation, maybe electromagnetic protection capability by 2035. These are examples. And then the constraints are those boundaries: cost, schedule, political, etc., that always influence the design of the system. So there are characteristics of effective vision are that it's imaginable, it's desirable, it's feasible, it's focused, flexible, and communicable. So, an effective vision, you should be able to communicate it to anyone. Think of it within just a few minutes. Think of it as an elevator pitch. You should be able to quickly and say, this is my effective vision. It should not be a paragraph but the characteristics, the vision statement itself should be one clear sentence or two. But the characteristics, certainly there's more thought behind it. From a desirable standpoint, it appeals to long-term interests of key stakeholders. It's realistic within achievable with hard work. It's focused. It translates to a tangible decision guidance. So needs, goals, and objectives definitions. Needs are what we want to do. What is our mission? A single statement that drives everything else. The goals are the strategies for accomplishing it. As I mentioned previously, here's a little more elaboration of that. It elaborates on the needs, which constitute specific expectations of the system. Goals address the critical issues identifying during the problem statement or problem assessment. Goals need not be quantitative or measurable at this point. They're goals. Now, the objectives are the tactics for accomplishing the goals, and they want to be specific. They want to be something that you can relate to and is measurable, and it should relate to a particular goal. There should meet these basic 4 criteria. They should be specific enough to provide clear direction. They should be measurable, quantifiable, and verifiable. They should be aggressive but attainable, challenging but reachable. And they should be results-oriented, focus on desired outputs and outcomes. So here's an example of NASA vision and mission. A vision of inspiration, a statement to accomplish. So the NASA vision to discover and expand knowledge for the benefit of humanity. Some of these are previous. They're not necessarily current or updated. The NASA mission then would be to lead an innovative and sustainable program of exploration with commercial and international partners to enable human exploration across the solar system and bring new knowledge and opportunities back to Earth. And then it continues. But you can see how the mission has kind of some specifics to that, and it relates to that, and then there's goals and objectives that relate to that. And this is the 2018 from the strategic plan. And then from that, you had strategic goals: discover, explore, develop, and enable. And with those, you have even more objectives from each of those goals. So you can see here how it continues to break down. And this is to really help you understand the process and the methodology that's used and thinking behind it. Here's some historical vision and mission statements: 1996, 98, 2000, so on. And you can see how they've changed over the years at NASA on the vision and also the mission, and how they have, kind of gone back and forth. And I didn't even include 2018, which we just reviewed. But you can see that, and if you continued this, you would see the goals and objectives that support the mission statement. So here's a 2004 example. The vision was to extend our reach with machines and people beyond low Earth orbit into deep space and to the objects of the solar system. Under such a charter, the mission of the agency becomes nothing less than opening up the entire space frontier to exploration, use, and development. And those are kind of visionary and far-reaching, but also obtainable. And if you decompose that into a mission statement, really advance U.S. scientific, security, and economic interests through a robust space exploration program. And I think you've seen this start to become a reality. And then you can get into, this is from the Constellation program way back in 2005, needs, goals, and objectives, how they further decompose those into specifics, into segments, elements, and systems, and so on. So with that, I'm going to switch over to my next presentation and just quickly give you a rundown on systems engineering from a technical writing, research papers, and master thesis. I wanted to work this in early on so it can help you with some of your work as you prepare towards your outlines for your research paper and so on. So these are the kind of questions for a research paper that you should think about. What is the problem? What is the issue or phenomena you're addressing, and why? What do you want to contribute, theoretically or practically? And who's going to benefit from this? Who's going to care about your research, and why are you doing it? And it could be just doing it for your own self, but I think you really research for the purposes of research should be something that can be shared and brings knowledge, additional knowledge, to your potential audience. What is the focus, and what do you not address in the paper? So it's just important to understand that the limitations of your research, and that you don't necessarily or cannot, given the time in one semester, to be able to do all the research in a particular area. And so in some cases you would say, this research paper is focused on this, and I'm not covering this aspects of the research. I will do that at a later time, a different research paper. So you want to be exactly, what exactly is or are the aims of your paper? What is or are the hypotheses of your research questions? And think about who your intended readers are, and what would they be specifically interested in, and why? And then what is new in your research or your paper, and where and how are you going to emphasize that? So in a research study plan, you plan and describe what you want to do to complete your research. List the stages of the project in a format table, indicate the deadlines that you set up, and discuss any particular challenges that you need to overcome, and use a Gantt chart to format your study schedule, in which we will go over later today. So this is the aspect of research rhythm and study planning, research analysis and design, being task oriented, and thinking about the products that have to be produced, and then overlaying that over with the tasks to be done. And these are the examples of that have been done in the past, and I did receive a lot of them today. Thank you. This is the AIAA, I believe, the conference format, and we've talked about this already. It should be conference ready, and part of this process is really to help you develop and mature your writing skills, and develop and mature your presentation skills. So an annotated paper or annotated outline is one where you begin with the introduction section. You annotate the outline, should begin with an introduction section, and underneath that section heading you should include 1 point for each. So it should be an attention grabbing hook to open your paper, a preview of the main points, or your thesis statement. So in essence, an annotated outline is you take all the different aspects, sections of your paper and the paragraphs or subsections, and you write a short 1, 2, 3 sentence of the intent of each of those sections. Excuse me. You don't want to go overboard in writing too much, but you want to write enough about each of the sections and the intent excuse me, of each of those sections. So you want to include, so each section heading should have at least 2 supporting paragraph headings under them, and then the intent of those supporting paragraph headings. Create a topic sentence for each paragraph. So this will help you with your flow. It'll help you understand how you want your paper to read, kind of the flow of your paper, and the intent of each section and paragraph and supporting paragraphs of each of those subsections. And so you want each of those, note that each 2 supporting points in each paragraph. And this will help you really focus and lay out your outline. And this is what I'll be looking for at the midterm for your annotated outline for your research paper. And then you end with a conclusion section. Annotated outline should end with a final section, title, conclusion, or summary. And underneath it you would have the section heading one and a point for each rephrasing your statement, concluding details, and then a final line or clincher which reinforces your research. Excuse me. So the master thesis, and perhaps Olga's already gone over this, is slightly different but similar in that you, for your thesis planning, you want to demonstrate that your master thesis topic addresses a human space exploration mission or design challenge. Demonstrate an organized study plan is in place to accomplish your master thesis research, analysis, and design to solve the problem. You want to demonstrate that the master thesis research, analysis, and design provide an appropriate solution to space exploration and design challenge. You always want to have technical truth, and always make sure that you have proper technical writing, grammar, and spelling. It's very important that you always keep that in mind. And what I mean by technical truth is if you don't know the answer to something, don't bluff the answer. Say you don't know. You want to stick to the facts, stick to the technical truth. This is the structure of a master thesis. You can read through that. I'm sure you've already gotten some of this from U of H as well. You have your title page, your abstract, and usually the abstract is written after you've done all your work and all your writing. Or you can write a draft, then come back to it after you've finished. So it's basically a summary of the design work. This is some key points about the introduction. What is the general design area? Why is the topic relevant? And what is the scope of your research or your master thesis? You should have a master thesis statement, and it should be a couple of sentences. And the statement can take a form of a hypothesis, a research question, project statement, design statement, or goal statement. And this thesis statement should capture the essence of your intended project. And also it should cover some aspects of the boundaries and constraints, your vision, mission, goals, and objectives. You also want to cover your research analysis, all the great work that you will be doing or have done, and you want to capture all that. You certainly want to include the systems engineering results, your ConOps, your functions, your stakeholders, your requirements, all of that information. Include any constraints, assumptions, and design criteria, as well as evaluation criteria. Include your citations of your data sources. Do not include results and decisions of results here. And then you get into your analysis and design discussion. That's really getting into the details of it. You may include your design reference mission here, the trade studies you've done. It really discusses how they fit in the framework of your thesis. You may include here your volume and mass allocations and analysis, any logistics analysis, design and evaluation criteria, your design options and trade studies, etc. And then your list of references. I think you all know and understand that. So this is kind of a general outline in which in order to write your thesis. Make an outline of your master thesis before you start. Outline your salient design points. Develop your annotated outline. Begin to define your figures and tables. Capture your figure captions, research analysis, discussion of your analysis and case studies, your design rationale and discussions. Go back then and write your introduction and your abstract and your bibliography. So in summary, plan time for writing. I think part of this is really getting you into a rhythm, understanding the importance of outlines, as well as annotated outlines, and throughout the process, document your design system engineering results. That's why the weekly statuses can be an advantage to you if you do it in a way that you can then capture knowledge as you go through your research, and then be able to later on take that and not necessarily start from scratch, but fold it into your annotated outline and building as you go. So it's important that you document your analysis and your trade studies, that process that we discussed earlier, document your designs as you go through the semester, and then the aspect of technical truth, and again, grammar and spelling. So that midterm assignment, which you already know, is due in October 5th, and that would be an annotated outline as we had just discussed. So with that, let me stop recording.